On July 18, 2022, archaeologist Darren Duke and Cornell researcher Thomas Urban were riding across the Utah Test and Training Range west of the Great Salt Lake when Urban saw a pattern in the pale desert surface. At first it looked like ordinary disturbance in the mud, then the spacing became regular. Left, right, left, right. He asked the driver to stop. Urban stepped out into a landscape that appears almost empty today, a military range of salt, dust and heat. But directly beneath his boots were the outlines of bare human feet. Some were adult-sized, others belonged to children. Many were so faint they vanished as the ground dried, appearing only when moisture darkened the sediment. The team returned with ground-penetrating radar and discovered that the visible tracks were only a fraction of what remained underground. In total, they documented 88 footprints. The most likely age was about 12,000 years. That meant these people had crossed the mud when the Great Salt Lake Desert was not a desert at all. It was a wetland, a place of shallow water, reeds, birds, and human movement at the end of the Ice Age. And less than half a mile away, another excavation had already produced evidence that seemed to push a familiar human habit thousands of years deeper into the past. The Great Salt Lake is often treated as a strange but simple body of water, a shallow inland sea famous for salt, brine shrimp, and birds. But the lake is only the surviving center of a much larger vanished world. Its predecessor, Lake Bonneville, once covered much of western Utah and extended into parts of Nevada and Idaho. At its highest recognized shoreline, water stood roughly 1,000 feet above the modern lake. Places now occupied by roads, suburbs, salt flats, and military installations were once beaches, marshes, islands, or deep open water. As that water retreated, it left layers: mud over gravel, salt over hearths, cave dust over baskets, shoes, bones, and human waste. The modern lake has spent thousands of years covering evidence, preserving evidence, and then revealing it again when the water moves. Quick second. If investigations like this are landing for you, subscribe. It costs one click, and it helps me keep doing the deep research these stories deserve. Now, let's go back to the footprints, because they are only the beginning. The first discovery. A family crossed the vanished marsh. When Thomas Urban saw the first marks from a moving vehicle, he did not immediately know they were human. What caught his attention was the alternating sequence. Natural cracks do not normally form a walking rhythm. The next day, Urban, Darren Duke, and their colleagues surveyed the area using ground-penetrating radar, a method Urban had also used to study ancient ghost tracks at White Sands in New Mexico. Beneath the surface, the radar detected impressions that could no longer be seen with the eye. The final count reached 88 individual footprints made by adults and children. The tracks had formed in wet sediment and were later filled and sealed. The team concluded that the most reasonable explanation placed them near the end of the Pleistocene, around 12,000 years ago, when this part of Utah still contained extensive wetlands. Imagine standing there then. Your feet sink slightly into cool mud. Waterfowl lift from the reeds. Children step into the prints of adults or wander beside them. There are no wagons, no roads, no written names for the place. Then the marsh dries, the impressions disappear under sediment, and 12 millennia pass. The eerie part is not simply their age, it is the social scene preserved in them. Stone tools can be carried, traded, or abandoned. A footprint records a body in a specific place at a specific instant. These were not isolated hunters represented by a single spear point. Adults and children moved together across a living wetland. Yet the trackway does not reveal where they were going, what season it was, or whether the group belonged to one family or a larger traveling community. The specialists can recover direction, size, and sequence, but not intention. 88 steps survive. The destination does not. The second discovery. Tobacco was already beside the fire. In 2015, Darren Duke's excavation team was working at a site now called Wishbone, also in the Great Salt Lake Desert. They exposed a small human-made hearth, darkened by charcoal and surrounded by the remains of ordinary camp activity. There were stone tools. There were the bones of ducks that had apparently been eaten. Then, inside the hearth material, researchers identified 4 charred seeds belonging to wild tobacco, Nicotiana attenuata. Radiocarbon evidence placed the occupation at roughly 12,300 years ago. Before Wishbone, the oldest widely discussed direct evidence of tobacco use in North America came from nicotine residue in pipes dating to about 3,300 years ago. The Utah seeds pushed documented human association with tobacco back by approximately 9,000 years. This does not prove those hunter-gatherers smoked. No pipe was found beside the fire. The seeds could have arrived with leaves and stems that were chewed, sucked, burned, handled medicinally, or used in a way that left no recognizable tool. Tobacco is not a major food source, which makes its presence beside a Pleistocene hearth unusually difficult to dismiss as an ordinary meal. Put the 2 timelines side by side. The footprints date to approximately 12,000 years ago. The Wishbone hearth dates to approximately 12,300 years ago. The locations lie less than half a mile apart. The start dates match. The landscape matches. One site preserves people moving through the wetland. The other preserves what people carried to the fire. Researchers can identify the species and date the charcoal, but the exact behavior remains unresolved. Was this medicine, ritual, pleasure, insect control, or an accidental inclusion? The earliest known tobacco-associated campsite in the Americas gives us the object, the fire, and the people. It does not give us the reason. The third discovery. The cave kept 11,000 years. In 1949, University of Utah archaeologist Jesse D. Jennings entered Danger Cave near Wendover, less than 2 miles from the edge of the Bonneville salt flats. Others had examined the cave earlier, but Jennings approached it with unusually controlled excavation methods for the time. Layer by layer, his crews descended through dry sediment that had accumulated for thousands of years. The cave measures roughly 60 by 120 feet, and deposits in parts of it reached about 13 feet deep. The dryness preserved materials that would normally rot: cordage, basket fragments, leather, wood, netting, seeds, plant fibers, and human paleofeces. Excavators recovered more than 2,500 chipped stone artifacts and over 1,000 grinding stones, along with remains from dozens of plant species and many animals. Evidence showed repeated human use extending back roughly 11,000 to 12,000 years. The discovery rewrote the picture of early Great Basin life. Instead of people briefly passing through an empty desert, Danger Cave revealed generations adapting to a difficult environment with nets, baskets, grinding equipment, hunting tools, and detailed knowledge of local plants. Modern survivalists arrive with steel blades, synthetic rope, water filters, and packaged food. These communities endured without any of them. But the layers contain gaps. Occupation was not continuous. People came, disappeared, and returned. Some deposits are separated by long intervals, and the reasons remain uncertain. Climate shifts, water availability, animal movements, and seasonal travel may all have mattered. No wall inscription explains when the cave became useful or why it was abandoned again. To this day, the cave still holds unopened evidence. The known objects answer how people survived. The empty intervals ask a darker question. What happened in the centuries when no one came back? The fourth discovery. Their shoes pointed north. In 1930 and 1931, archaeologist Julian Stewart excavated caves at Promontory Point on the northern side of the Great Salt Lake. Inside the dry chambers, he found an extraordinary collection of perishable material: bows, arrows, mittens, fragments of bison robes, gaming objects, and hundreds of moccasins. Many of the shoes were heavily worn. Some were tiny, made for children. Decades later, University of Alberta archaeologist Jack Ives and a new team returned to the Promontory caves. Between 2011 and 2014, they recovered additional artifacts and re-examined Stewart's collection. The moccasins were not made in the style archaeologists expected from nearby Fremont communities. Their construction strongly resembled footwear traditions associated with Dean-speaking peoples farther north, including ancestral populations related to later Apachean groups. Indigenous specialists, including Tsutina elder Bruce Starlight, recognize the technological tradition. The dates cluster around the 13th century, a period when many Fremont settlements were under stress or being abandoned. Yet the promontory occupants appear to have been thriving. The caves contain evidence of bison hunting, hide processing, games, food abundance, and numerous children. This was not merely a desperate refuge. The finding opened a major migration question. Did Dean-speaking ancestors move south through the Great Basin before some continued toward the southwest? Were the Promontory people direct ancestors of Apachean communities, close relatives, or a neighboring population sharing northern traditions? Material culture can refresh connections, but language leaves no fossil. The shoes are still here. Their seams, wear patterns, and sizes can be measured. They show men, women, and children living inside those caves. But the people left no written account of where they came from or where they went. The footwear points north. Their final trail disappears south of the lake. The fifth discovery. The cave sounds like children. When Jack Ives' team reopened the Promontory excavations, they did not find only weapons and hunting equipment. They found the remains of domestic life. Small moccasins, gaming pieces, worked hide, and objects associated with repeated social activity. In the first instant, this changed the emotional character of the site. The cave was not simply a temporary hunting station occupied by adult men. It had held families. Analysis of moccasin sizes allowed researchers to estimate the demographic range of the population. The assemblage included footwear for people of different statures, including children. The caves also produced evidence of feasting and gaming. In other words, while some neighboring societies were experiencing instability, this group gathered, ate well, processed valuable bison hides, raised children, and played. That creates an unsettling contrast. Archaeology often explains migration through crisis, drought, hunger, violence, or environmental collapse. But the Promontory record does not look like the debris of a starving group barely surviving. It looks energetic and successful. Scientists still debate exactly how this community fit into the larger transition occurring across the region. Their material culture is distinct, their northern connections are strong, and their occupation overlaps with the decline of Fremont lifeways. Yet there is no single layer showing a confrontation, a takeover, or a clear merger. Tell me in the comments what you see in that evidence. A migrant community passing through, or a new population establishing itself while an older regional order was fading. The children's shoes prove families were there. They do not tell us what those families witnessed outside the cave. The sixth discovery. 1,000,000 bones filled one chamber. In the mid-1990s, paleontologist David Madsen and zooarchaeologist Donald Grayson excavated a single cubic meter of sediment from Homestead Cave, west of the Great Salt Lake. What emerged was almost impossible in scale. An immense concentration of small animal remains, part of a deposit estimated to contain roughly 1,000,000 bones. Owls were largely responsible. Over thousands of years, birds of prey nested or roosted near the cave, swallowed rodents and other small animals, then coughed up compact pellets filled with bone. The dry environment preserved layer after layer. Researchers could identify changing populations of mammals and birds, turning the cave into a biological record of climate and habitat through time. Tens of thousands of bird bones alone required years of analysis. A modern environmental survey might require traps, satellite data, weather stations, and decades of observation. Homestead Cave stored a natural census without instruments. Each jawbone and tooth recorded what could survive near the lake at a particular time. But the record is not perfectly straightforward. Owls hunt selectively. Species move as temperature and vegetation change. The cave's chronology must be reconstructed from sediments and dating, and each layer represents an accumulation rather than a single night. Scientists can see ecological transitions, but converting those bones into an exact year-by-year climate story remains difficult. The chamber is a library written in skeletons. It confirms that the Great Salt Lake Basin repeatedly transformed around its inhabitants. The unanswered question is how many ecological collapses are hidden in the gaps between one layer of bones and the next. The seventh discovery. The rocks are alive. At Bridger Bay on Antelope Island, falling water exposed rounded, reef-like structures along the shoreline. Visitors sometimes mistook them for ordinary stone. Scientists identified them as microbialites, carbonate formations built with the help of microbial communities. Similar structures preserve some of the oldest evidence of life on Earth. Researchers collecting sediment and breaking apart portions of these microbialites recently found something unexpected inside them. Thousands of nematodes, microscopic roundworms, representing several species. Scientists had suspected nematodes might live in Great Salt Lake sediments, but no one had previously recovered them there in confirmed numbers. The discovery expanded the known food web of an ecosystem long described as biologically simple. The lake's salinity can reach levels far beyond ordinary freshwater tolerance. In one experimental comparison, researchers exposed the laboratory nematode Cenorhabditis elegans to Great Salt Lake conditions, roughly 50 times saltier than its typical environment. The native worms, however, were living inside protected microbial structures, where chemistry, bacteria, and tiny pore spaces may create a refuge. The mystery is not whether the worms exist. They do. The mystery is how the entire hidden community functions. What do the nematodes eat? How long have they occupied the microbialites? Did they evolve locally, arrive with birds, or persist from a wetter phase of the lake? These formations are still visible now. You can stand on the shore and see what resembles dead rock. Inside, an ecosystem is moving through microscopic tunnels. The eighth discovery. White terraces grew overnight. In late 2019, Great Salt Lake State Park staff refreshed strange white mounds forming near the marina on the southeastern shore. Ranger Allison Thompson watched the features grow and contacted the Utah Geological Survey. Geologists arrived expecting ordinary salt deposits. Instead, they found terraced crystalline mounds formed from mirabilite, hydrated sodium sulfate, sometimes called Glauber's salt. Cold, relatively fresh groundwater was rising through the lakebed. When the mineral-rich water reached winter air, mirabilite crystallized around the spring outlets. Some mounds grew into layered terraces, then sealed their own water source. The spring pressure shifted, and a new mound appeared dozens of yards away. Utah geologists noted that modern examples of this quality are rare, with better-known counterparts in places such as the Canadian Arctic. The first site is deeply unnatural. Bright white mineral towers beside grey water, steaming or dripping in winter cold. They look permanent, but warmth destroys them. As temperatures rise, the mirabilite loses water and breaks down into powdery thenodite. The architecture collapses almost as quickly as it formed. Researchers understand the chemistry, but the subsurface plumbing remains only partly mapped. Where exactly does the groundwater travel? Why do outlets emerge in particular lines? How long has this process occurred beneath higher lake levels, invisible to everyone? The formations appear because the shoreline has retreated far enough to expose the springs. The lake did not suddenly begin making them. We simply reached the moment when the water stopped hiding them. The ninth discovery. Islands rose from the lakebed. As Great Salt Lake levels fell, researchers began noticing circular mounds and raised features offshore and across newly exposed margins. From above, some looked like small islands, appearing where charts showed only shallow water. University of Utah geologist William Johnson and other scientists investigated whether pressurized groundwater moving through buried pathways was pushing sediment upward or building mineral structures beneath the lake. The working idea is a hidden plumbing system. Fresh groundwater travels underground, reaches weak points in the lakebed, and discharges into dense saline water. Sediment, minerals, gas, and microbial activity may combine to produce rounded mounds. But the exact formation mechanism has not been fully resolved, and different mounds may not share the same origin. Imagine approaching one by boat when the lake is higher. Nothing appears on the surface. Beneath you, fresh water may be moving through the floor of a salt lake, feeding a mound in darkness. Then the water level drops, and an island seems to materialize. Official science has a plausible mechanism, not a complete map. The underground channels are difficult to observe directly. Their flow rates, ages, and connections to distant aquifers remain active questions. What else is rising under the parts of the lake that still have water? If the current low shoreline revealed these mounds, then the remaining lake may be concealing an entire field of them. The 10th discovery. The lake returned its ships. In 2020, powerful winds and low water exposed the remains of a wreck along the Great Salt Lake shoreline. Then, during the extreme decline of 2022, another historic vessel became clearly visible. This one had belonged to the Southern Pacific Railroad fleet, used to help construct and maintain the Lucin Cutoff, the railroad route driven across the lake in the early 20th century. The wreck had first sailed roughly 120 years earlier. For decades, water and mud hid its frame. As the lake fell to record low elevations, timbers emerged into open air. Utah officials and historians noted that the Great Salt Lake may contain dozens of wrecks from approximately the last century and a half, including workboats, ferries, recreational vessels, and craft whose identities are uncertain. The discovery moment was not a deep-sea expedition. No diver descended into black water. The lake simply withdrew. That makes identification surprisingly difficult. Boats were rebuilt, renamed, repurposed, stripped, and abandoned. Historical records are incomplete. No name on the bow, no intact registration plate. Not a single surviving line may connect a wreck to the person who last stood on its deck. The timbers are still down there right now, some exposed, others buried in sediment. Every year of low water may reveal another section. Every storm can cover one wreck and uncover another. And that leaves the final question hanging over the shoreline. Is the lake returning known history? Or are some of those hulls vessels that disappeared without leaving enough records to identify them at all? The Great Salt Lake does not rewrite history by producing one impossible object. It changes history by removing the assumption that this landscape was empty. The footprints show adults and children crossing a wetland 12,000 years ago. The Wishbone hearth places tobacco beside a human fire at roughly the same time. Danger Cave records thousands of years of desert knowledge in baskets, nets, tools, seeds, and preserved waste. The Promontory moccasins trace a population whose northern connections may illuminate the movement of Dean-speaking ancestors. Homestead Cave holds an environmental archive made from almost 1 million bones. Microbialites shelter an ecosystem scientists had overlooked. Mirabilite terraces reveal groundwater forcing its way through the floor of a salt lake. New islands expose plumbing no map fully shows. And the retreating water returns ships whose names may already be lost. None of these discoveries requires a conspiracy. The documented reality is stranger and more important. The basin keeps records in materials historians rarely use. Footprints that appear only when wet, seeds burned in a fire, shoe seams, owl pellets, living stone, temporary crystals, and wooden hulls emerging from mud. You can still go to the Great Salt Lake and stand beside parts of this evidence. The microbialites remain on the shore. The caves still hold sealed deposits. The mounds may return in cold weather. More wreckage waits beneath sediment. And under the military range, invisible footsteps continue beyond the point where archaeologists stopped excavating. History is usually imagined as something written and stored. Here, it is submerged, crystallized, buried, and occasionally exposed by drought. So when the lake pulls back again, what will appear next? And will we recognize what it means before wind, salt, or water hides it for another 1,000 years? Share this investigation with someone who still thinks an empty desert has nothing left to say.